I'm Anna Scaife. I'm a professor of radio astronomy at the University of Manchester, and I'm going to be talking to you this morning about the Square Kilometre Array project. I'd like to start by thanking the organisers. It's a real pleasure to be invited to speak at the GNU Radio conference. I wish I could be there with you in North Carolina, but hopefully this virtual presentation should be just as good. Before we start, I would like to invite you to think back pre-pandemic to what you were doing on the 12th of March in 2019. Maybe not even on the 12th of March, maybe just in March 2019. It seems like a lifetime ago. Well, for these people, what they were doing is signing a treaty to form the world's first intergovernmental organization for radio astronomy, the Square Kilometre Array organization. And these are the founding countries of the SKA treaty. From left to right, you can see representatives from the UK, China, Portugal, Italy, South Africa, the Netherlands, and Australia. And since they signed this document in 2019, the treaty has been ratified and the Intergovernmental Organization for Radio Astronomy came into being at the beginning of this year. However, the SKA project is larger than just the founding treaty members. In fact, there are 16 partner countries in the SKA project, and they've come together to build the largest radio telescope in the world. And the motivation for this is to answer some of the key outstanding questions in modern astrophysics. For example, when did the first stars and galaxies in our universe form? So we know how old the universe is, but we also know that when the universe first formed after the Big Bang, it was composed almost entirely of neutral hydrogen. It was very dark, very empty, and we refer to that period of cosmic history as the Dark Ages. And then at a particular point in that cosmic history, the very first stars and galaxies began to form, and they created ionization in that neutral hydrogen. And that's what you can see in this simulation on the top left, these bubbles of ionization spreading out and eventually filling the whole universe until it looks more like it does in today. Stars and galaxies in every direction. The question is, exactly when in cosmic history did this re-ionization occur? And what were the processes that were underlying it? And this is one of the key driving questions for the SKA telescope. We refer to this as the epoch of reionization science case. And you can do this in the radio regime using the Doppler shifted spectral line that comes from the neutral hydrogen atom. But you need a very, very sensitive telescope in order to do it. In fact, it needs to be sufficiently sensitive that it has a square kilometre of collecting area in order to achieve that sensitivity, and hence the name Square Kilometre Array. Some of the other driving science cases for the SKA include the detection and mapping of gravitational waves as they pass through our own galaxy. Some of you may be familiar with the results from the LIGO experiment, which made the first direct detection of gravitational waves relatively recently. The SKA works in a similar way to the LIGO experiment, but instead of using physical baselines on the ground to detect the interference patterns from those gravitational waves, it actually uses networks of highly precise clocks, astrophysical clocks known as pulsars, which are rapidly rotating neutron stars. And by measuring the timing of those repeating, pulsing neutron stars, which are very, very precise, it can track the passage of gravitational waves through our galaxy, which opens up an entirely different regime of gravitational wave frequency from, for example, the LIGO experiment. Another science case that drives the SKA is understanding where magnetic fields come from. Now, magnetic fields are one of those things that are completely ubiquitous in astronomy. We see them on the very smallest scales, from where they influence the formation of stars, to the very largest scales where they govern the evolution of galaxies. But we don't know what the origin of those magnetic fields is. And so highly sensitive polarization measurements with the SKA will allow us to constrain that. And then finally, a case that many people like is the search for extraterrestrial intelligence. Are we alone in the universe? Now, there are many ways to address this question experimentally, but one of the primary methods for the SKA is to use the very fine spectral resolution of the instrument in order to measure molecular emission lines from molecules that indicate the presence of life on other planets. To address the science goals of the SKA actually needs more than one telescope. And so, in fact, the SKA Observatory is building 2 telescopes. The first of these is a centimetre wave array, which you can see on the left-hand side here. And the second is a meter wave array on the right-hand side. And these 2 telescopes operate independently and address different science cases for the SKA. And in fact, because of the different technologies involved, and because of the different parameters of the science cases that they're designed for, they're also not in the same place. So we refer to the SKA as 1 observatory, 2 telescopes, and 3 locations. I'll come back to the 3rd location later on. So where do you build a telescope like the SKA? Well, for radio instrumentation with these kinds of sensitivities, you need to build it somewhere where man-made radio frequency interference is going to be minimized. And so the SKA telescopes are going to be built in 2 of the most radio quiet places in the world. The first of these is in the northern Cape of South Africa in the Karoo region, where the South African government has instituted a protected astronomy reserve. And in this location, the telescope that's going to be built is the centimetre wave telescope of the SKA, what we call the mid-frequency array. And this is an interferometric array, so it is an array of dishes. You can see them just popping up out of the landscape there. Now, in this artist's impression, you can see that the design for the dishes is an offset Gregorian design. So there's a carousel of receivers that sits in that cradle attached to the main dish by the receiver arm there. And in total, there are going to be 197 of these dishes spread across South Africa and up into neighbouring Namibia and Botswana. And those distances are necessary in order to achieve the resolution that we want to address the science goals of the telescope. Now, in practice, of course, maintaining a radio quiet area over those kinds of distances is extremely difficult. And whilst you might have a protected astronomy reserve around the main concentration of dishes, of course, when you talk about those hundreds of thousands of kilometre distances, you also need to think about the wider environmental factors that are affecting your radio environment. And of course, as we know, the main factor that affects the level of radio frequency interference is population density. And we can see that here in this map of background radiation at 130 megahertz across the world. And what should be evident is that in the northern hemisphere, there's a lot of background radiation. You can especially see that bright concentration over continental Europe. But in the southern hemisphere, it's distinctly more quiet. And I've in particular highlighted South Africa here and Western Australia as particularly radio quiet areas. And that, of course, is due to the comparative population density in those regions. So I'd just like to put that into context for people by letting us think for a moment about the population density in North Carolina. So if we think about the number of people in North Carolina, and in particular in Mecklenburg County, where Charlotte is, you can see that there's roughly about 1,700 people per square mile in Mecklenburg County. And of course, that's because Charlotte forms a large part of the county there. In terms of the number of people per square kilometre, that's about 1,000 people per square kilometre. Of course, North Carolina is not the most heavily populated state in the US, nor is it the least populated. But let's just compare that number for a second to the population density in the Karoo region in the Northern Cape of South Africa. So if we look at the population density in South Africa, you can see that it's heavily concentrated around the coasts and into the northeast there. In the Karoo region, and especially in that protected astronomy reserve, the population density is somewhere between 0 and 4 people per square kilometre. So it's extremely low, and that's very important for maintaining that RFI quiet area over large contiguous distances. And you can see the positions of the different dishes that are going to be spread out across that region for the Scaife mid-frequency array. However, the second telescope of the Scaife is going to be somewhere even more radio quiet than the Karoo region of South Africa. Now, to get to the second telescope, we have to go all the way around to the other side of the southern hemisphere, out into Western Australia. Now, Western Australia is going to be the site of the low frequency telescope. So this is a meter wave array, and the technology is really quite different here. You can see that we don't have solid dishes. The array is built up of islands of dipole antennas, and these are, we call them Christmas tree antennas because of the shape, and that makes them a very broadband, low frequency antenna. Now, these antennas are going to be located in an area known as Murchisonshire in Western Australia. It's an area of about 50,000 square kilometres. There are no towns. It's mainly used for sheep farming, and it has a population of 110 people, which gives it a population density of 0.002 people per square kilometre. So extremely low. 50,000 square kilometres is an area roughly the same size as the Netherlands in Europe, or the state of West Virginia in the US. West Virginia, of course, being famously home to the Green Bank Telescope, the largest fully steerable single dish telescope in the world. However, the average population density in West Virginia is 29 people per square kilometre, which actually makes it one of the lowest population densities in the US, but still significantly higher than Murchisonshire with 0.002 people per square kilometre. Being located in an area of such low population density and hence very radio quiet environment is vitally important for the low frequency telescope of the Scaife. These stations of antennas that you can see here are phased arrays of the dipole antennas, and so effectively they form the same kind of thing as an individual dish in the mid-frequency array. And they are the technology that will be used primarily to address the key science goal of detecting and mapping the epoch of reionization when the first stars formed. In total, when it's fully constructed, there will be 130,000 of these dipoles clustered into stations and spread out across the red deserts of Western Australia. What I've been showing you up to now are, of course, artists' impressions of the telescopes. And the full construction of the telescopes isn't expected to be finished until 2027. But of course, there is hardware already on the ground. And here is the first 64 dishes of the Scaife mid-frequency array in South Africa. This is known as the Meerkat Telescope. Of course, the beauty of interferometric radio telescopes is that you don't have to have finished the full array before you can start using them. As soon as you have 3 dishes on the ground, you've got a calibratable array, and every time you add a new dish, you just expand your array. And you can do that progressively until you have your full 197. Now, the Meerkat Telescope is the precursor to the full mid-frequency array of the Scaife, and it's already producing science. And the science that it's producing includes some of the most beautiful radio images of the universe that we've seen to date. This was one of the earliest images produced by the Meerkat Telescope. This is the center of our own galaxy. One of the advantages of building a telescope in the southern hemisphere is that the center of our own galactic plane, the Milky Way, is visible from the southern hemisphere. You can see it from the northern hemisphere, but you really have to, you're really tilting over the horizon. But from the southern hemisphere, it's just perfect. And this image shows so much detail of the different star formation and the stellar evolution processes that are going on our own galaxy. It's really quite remarkable. So some of the things you might notice here are the envelopes on the left-hand side around those star-forming regions, and also these beautiful trails of radio emission, those like spikes or just slithers of radio emission coming off our galaxy. And again, that's thought to be due to star formation, and it hasn't really been visible in any previous images of the galactic center. But the Meerkat Telescope has made that possible. And of course, our own galaxy isn't the only thing we can see. One of the other really beautiful things that's come out of the Meerkat Telescope already is a very detailed look at the dynamics of what we call active galactic nuclei. So these are galaxies that are quite different from our own. They are not star-forming galaxies like the one that we live in. These are basically a supermassive black hole, which is what you can see as a sort of a point in the middle of this structure. A supermassive black hole powering enormous jets of ultra-relativistic particles, so electrons, positrons, protons, and shooting those jets out into the surrounding intergalactic medium where they're interacting with their local environment. And that's what you can see in those beautiful dynamics of the jets there. What's remarkable about this image are those very narrow bands of emission that jump, sort of form a bridge from one jet to the other. And those haven't been seen before in radio galaxies. And so this was really quite a remarkable picture, showing a level of detail that we haven't previously been able to achieve because we haven't had the sensitivity, we haven't had the resolution. Another very beautiful thing that we see is, again, with these active galactic nuclei, these supermassive black holes, you can see that the jets in this case are not symmetric. They don't sort of come out one on either side of that central supermassive black hole, but they have this kind of X shape. And this has been seen before, but not in so much detail. And when you don't have the detail, you really can't constrain the underlying physics of what's happening. And so the Meerkat's data are suggesting that the X shape that we see there is old radio emission. So this is populations of ultra-relativistic electrons that are losing their energy because they're much older than the newly accelerated electrons. And those newly accelerated electrons are very close to the central supermassive black hole. Now, the other reason that I wanted to highlight the South African array in particular is because the very first demonstrator instrument for the telescope, of course, we take a number of staged development milestones when putting together telescopes on this scale. One of the very first stages of development for the South African arrays was something called the Phased Experimental Demonstrator, or PED. And for the PED, the first light traces were actually enabled by GNU radio using a software radio board. And thanks very much to my colleague Ludwig. These are two of those traces. These aren't the interferometric traces. These are from single antennas, and this is just a trace looking at the sun. But I thought it would be interesting to include where GNU radio has contributed to the development of the SKA. So before I talk about the computing behind the telescope, because if nothing else, the SKA is a software-enabled radio telescope, I wanted to talk a little bit about how interferometers work, just for those people in the audience who aren't so familiar with radio telescopes particularly. And in particular, I want to talk about radio interferometers because that's what we build with the SKA. We build these arrays of radio antennas. So at the bottom here, you can see a picture of a telescope that might be familiar to a few people. This is the Very Large Array in New Mexico. And this is a very famous, very well-established radio interferometer. And when we use a telescope like this, it's not the signals from the individual dishes that we are taking, but it's the combination of signals from every pair of dishes in the array. And what we do is we correlate the signals from each each pair of dishes. We refer to a pair of dishes as a baseline. And the correlation products, which we refer to as visibilities, basically give us a measurement of the amount of power on a particular angular scale on the sky, which is the same as a spatial Fourier frequency. Now, the dishes that are close together give us the larger angular scales, so the large scale emission on the sky, and the dishes that are further apart give us the larger Fourier frequencies, which correspond to the smaller angular scales on the sky. So as you increase the number of dishes in your array and you put them further and further apart, what you're doing is you're increasing the resolution of your instrument. What this means is that for radio interferometers, what we are measuring is not a direct image of the sky. So for neither the mid-frequency or the low-frequency arrays, we don't get an image as a direct output from the telescopes in the same way that you might do from an optical or an infrared telescope. So there's a significant amount of computer processing that needs to be done in order to convert the signals into a format that is usable for individual astronomers in order to address their science goals. And of course, that requires the signals to be digitized at a very early stage in the signal processing. And that's done at the antennas for the SKA. So this level of digitization, and given the number of antennas on the ground and the size of the arrays, which determines the time sampling of those signals, means that not only will the SKA be the world's largest radio observatory, but it's also one of the world's biggest big data machines. So I'd like to take a moment now and talk about the processing that sits behind a telescope like this, because the SKA really is a software telescope. I'm going to talk you through the different stages of signal processing within the signal chain from the telescopes. Digitization is performed very early on within that signal chain. And so the signals that come out of the telescopes are transmitted over optical fiber. And at this point, we have data rates coming out of each telescope of about 10 terabits per second. And they go to what we call central signal processing. Now you'll notice here that there are signals going into central signal processing and coming out. And of course, that signal coming out is our clock signal, which we use to synchronize the data from each of the individual dishes or from the stations of antennas on the ground. And that synchronization is extremely important because we need to be able to correlate the signals with very, very high precision. So our clock signal is at the level of an atomic clock. And we synchronize our signals in order to perfectly compensate for the physical distances between the antennas. Now, that's really for doing the image processing, but we also do a time domain signal processing for astronomical signals that have a time dependence that happens on very, very rapid timescales, so micro to millisecond timescales. And so for those data, we do an ordering and a compression or averaging in the data in order to try and reduce the signal volumes or the data volumes at this point. The image domain data, once they're synchronized, have to be correlated. And the correlation actually does the opposite. It increases the volume of data. And we end up with an output that's actually proportional to the square of the number of dishes in our array rather than linearly proportioned. So the data rate here is really very high. But the objective is that we then send it to what we call science data processing. And this is where we form the images from those correlated data products. And that image formation is a Fourier inversion. It also includes a deconvolution process. And we produce an image product that's not just an image, but is actually a cube, because this is multispectral data. So we can have 16,000 frequency channels across the SKA bands. And so astronomers actually receive a cube which has an image for each one of those frequency bands. And of course, those data products then need to be shipped around the world to the teams of scientists working on the different science objectives of the SKA. And that in itself is quite a challenge. These individual data products are somewhere between a quarter and half a petabyte each in size. So the individual telescopes are producing about 300 petabytes of data each per year in the compressed data products. We can also think about those signal chains in terms of their geographic location. The original idea for the SKA was to place the central signal processing very close to the antennas itself. In fact, it's now been moved into the same locations as the science data processing, which for the mid-frequency array is Cape Town, and for the low-frequency array is Perth. The processing that's required in the science data processor is extreme, so approaching half an exaflop of computing for this volume of data. And again, we're talking about hundreds of petabytes a year of data coming out of these instruments, which then we have to ship around the world, of course, to all of the different partner countries and to the scientists in those countries. So in fact, there are dedicated submarine cable links actually costed in to the project itself in order to do that. I'd just like to take a moment to put into context how large the data volume coming out of the SKA is. So from each telescope, we expect to be storing about 300 petabytes of compressed data products per year, so 600 petabytes in total. Scientifically, that's very large. So the largest radio telescope archive in the world at the moment comes from the LOFAR telescope, which is a low frequency array that spreads across a lot of Europe. And LOFAR is storing about 25 petabytes of data per year. For particle physics, the 5 big experiments at the LHC at CERN produce about 73 petabytes per year. And so again, the SKA is significantly larger than these, but it's also a lot larger than most commercial data volumes. So the numbers that I'm showing here are from 2017. I apologize, they're slightly out of date, but uploads to Facebook are about 180 petabytes per year, and searches on Google are also just coming in around 100 petabytes per year. More recent numbers from Facebook show that Facebook produces about 4 petabytes of data per day, but it compresses that down to fit into the Facebook archive, which is called the Hive, which has a fixed size of 300 petabytes for Facebook. If you put that into context with the SKA, if we take the data rate out of the telescopes, that will produce about 250 petabytes of data per day. And we compress that down to produce 600 petabytes per year of a growing archive. So hopefully this can show you that the SKA is really big data in terms of both scientific and commercial data volumes. And so the technologies that we're having to develop to support the telescope are really at the forefront of what's being done in this kind of area. Now, the other question that people often ask is, how big is a petabyte? Because this is perhaps a volume of data that not everyone is familiar with dealing with. So how big is a petabyte? And the simple answer is that a petabyte is about the same size as 3.5 years of your life. So it's been estimated that if you recorded every second of your life for 24 hours a day, 7 days a week, in high definition for 3.4 years, then the video you produced would be about 1 petabyte. So a petabyte is about 3.5 years of your life. Other ways of looking at it is that your entire human brain can store about 2.5 petabytes of memories. And if you stored 4,000 digital photographs per day, every day, for your entire life, they would require about 1 petabyte of storage. So hopefully from those numbers, it should be clear that when we talk about 600 petabytes of data per year, year on year, we're talking about a lot of data. And of course, we have to get it around the world to individual astronomers. But if you give individual astronomers that kind of volume of data, what are they going to be able to do with it? Because, astronomers are just normal people, right? We don't have the capacity to deal with much more data individually than anyone else. And so the answer is that we have to create a network of data centers around the world in order to support the scientific community in using these data. Because, let's face it, we're probably not going to be downloading 300 petabytes onto our laptops. And so as part of the SKA project, one of the things that's being developed at the moment is a network of what are called SKA regional centers, which are the centers where the data will be archived and made available to astronomers, but also centers that will provide the computing for the individual astronomers to work on the data itself. And when we think about what's in those data, then it becomes a whole other problem, because being able to access the data is one thing, but being able to use it, and not only use it, but use it in a timely fashion, is another thing. So in those data cubes, the SKA is going to detect tens to hundreds of millions of different astrophysical systems. Now, most of modern astrophysics is built on what we call population analyses. So we need to see a large number of particular types of known object in order to understand the factors that govern their evolution and their origins. But to do that, we need to be able to extract those astrophysical objects out of the data cubes themselves. And we need to be able to do that, firstly, in an automated fashion, because there's simply not enough time for individual astronomers to go and look at that volume of data. But we also need to do it in a manner that allows us to also identify if there's something in those data cubes that we've never seen before. History teaches us that most new scientific facilities don't become famous for the thing that they were designed to do, but they become famous for the thing that they discover. So we need to make sure that whilst we automate our processing, we need to do it in a way that doesn't automate out the potential for discovery. To end this talk, I would like to bring you back to the UK, where I am, to my home, and to the Jodrell Bank Observatory. And the Jodrell Bank Observatory is perhaps most famous for being home to the Lovell Telescope, which you can see here, 76-meter radio telescope, originally built in 1957 when it was the largest radio telescope in the world. Of course, it's been overtaken these days. But the reason I bring you here is not because it's my home observatory, but because it's also home to the headquarters, the global headquarters of the Square Kilometre Array organisation, now the Square Kilometre Array Observatory, since its intergovernmental organisation status has been ratified. And the headquarters of the SKA sits just below the Lovell Telescope. You can see it in the foreground of this picture. Of course, it is completely finished these days. This photograph was taken over a snowy winter when the headquarters was being constructed. And this headquarters represents to the SKA what CERN is to the LHC. It is the global organisation and will be for the next 50 years of the lifetime of the telescope. So I do recommend, if you're ever in the UK, you are welcome to visit the observatory. There is a visitor centre and you can take a peek at the SKA observatory itself. And at that point, I will finish. I will be live for questions, but I'd like to say thank you for listening to my talk and enjoy the rest of the conference.
So, first of all, thank you very much. I was already hearing from people in the room that they're very impressed about the scale of this application, which I think is probably the first thing that hits many people. There's been some questions in chat, and I was wondering if you wanted to speak to any of those directly before I take questions here in the room.
So the questions in the chat, let me see. So there's some questions about synchronization, which I hope I've answered correctly. So the question is, what's the mechanism that the SKA is using for the synchronization signal? And I believe it's White Rabbit. Now, if there may be some domain-specific adaptation of that that's being developed, but I'm afraid that I don't work in that consortium, so I don't really know the details of it. But until someone corrects me, I'll say it's white rabbit. And then let me see. There was also a question about the use of AI on a more internal basis rather than just for the science. So for the management of the observatory and specifically for the science pipelines. And that's something that we're starting to think about at the moment, not only for the computing, but also for the maintenance of the arrays. But obviously it's something that we need to collect data on in order to be able to actually do that kind of AI. So that's the stage we're at the moment with that. Yep.
Great, thank you. Are there any questions from here in the room?
Hi, great presentation. I loved it. Great animations as well. My question is, how are you processing all the data? Like I was looking at the webpage right now and I see that you have CPU processors, but are you also mixing other processors like GPUs, FPGAs? I don't know if you can comment a little bit about that on the processing side. Thank you.
Yeah, so in fact, the central signal processing is mainly on FPGA. So that's all firmware. And then the science data processor is all GPU. So in fact, the cost per flop and in fact the power, the flops per watt is much better on GPU for this processing.
So you talk about these data cubes which have 64K frequency slots. So how big are they sort of horizontally, both in like pixels, I guess, and angles dependent of the sky?
Yeah, so I think, so in terms of pixels on the side of an image, so the images are 64K by 64K, which I think is roughly 1 or 2 degrees for the mid-frequency array. For the low-frequency array, it'll be significantly larger, something more like 5 or 6 degrees in an image. And then in the frequency resolution direction, I think the specifications have up to 128,000 frequency channels, but in practical terms, I suspect that people won't really use more than about 32,000 frequency channels. Yeah.
For those who are not in the radio astronomy realm, frequency channels, at least based on my understanding, has ended up mapping very similar to how we would consider an FFT bin, although there's quite a bit of subtlety that ends up stacked on top of that I've yet to learn. Any other questions from the room? None from here. So just one last check with the online side. This is the fun bit of chasing around a hybrid event. All we have is a confirmation that it is White Rabbit from somebody who's gone and searched. So good guess. There's also a question of where did the animations come from?
Oh, so in fact, I think all of the animations that I've used are in the media and press pack on the SKA Telescope website. So skatelescope.org. So, yeah.
Wonderful. Well, thank you very much again, Professor. And we wish you had been here, but hopefully GRCon will be a little bit more open in the future and maybe even a European event. So thank you very much.
Yeah, you're very welcome. Thank you again.